Screen recording. Oh dear, wrong button. All right, guys. So please, thank you. Jacob, we are 33. If we had a north pole of a magnet there, obviously remember these magnets would extend on. We would have between the two magnets, we would have a magnetic field traveling from north to south. Okay. So again, remember these magnets would be dipole. What we're going to do is we're going to take a wire, but I'm going to put an axis of rotation. So could you put in a dashed line? Okay. So here is our axis. And we are going to attempt to put a wire into this field. It's going to go parallel. Then also it's going to go parallel. Then it's going to travel like so. And then it's going to go parallel again. And then travel like so. And then parallel again. And hopefully I've drawn it nice and symmetrically. Doesn't really look that good, but that'll do. Now, let's throw some current into this loop of wire. Okay? So it's going to go in and around and return out. So I've drawn in my red arrows is the direction of my conventional current. The blue is the direction of that external magnetic field. There's going to be some Lorentz forces going on. But let's first off figure out this section. It's parallel to the field. So that's like placing your thumb same direction as your fingers. There's no perpendicular component there. Okay? So let's just highlight the stuff that's not important is right there. We could write F equals 0, F equals 0 because it's parallel. And the same at the top. Okay. And that's obviously our Lorentz force. There's no Lorentz force. But here's the important one. Let's look at the left side wire. We've got our current traveling into the page. We've got our magnetic field traveling left. Let's use our right hand Lorentz force rule. This section of wire is going to be forced upwards. Okay? So could you please draw an upwards arrow, and that's the direction of our Lorentz force. Okay? Then let's look at what happens over on the other side. We've got our current is now traveling sort of out of the page, or towards us at least. We've got, get that, oh gosh, oh boy. Just want to get that I somewhere else. We've got our magnetic field still in the same direction, and so now, thumb going that way, fingers traveling to the left, this side of the wire is going to get pushed down. Okay? So what we have is to the left of the pivot, we have an upwards force that produces a clockwise torque. To the right of our pivot, or at least our axis, we have a downwards force that also produces a clockwise torque. What we would see is that this loop would rotate clockwise. Clockwise. So there'd be a clockwise rotation. Now, we can do a couple of things. What do we want to do? At the moment, we have the maximum torque, but let's just write that the force equals B perp IL. All right? Now, generally, this loop will always be orientated so that the wire is always perpendicular to the field. Have a think. If we could visualize this loop rotating, it's always, the wire is the thumb, it's always perpendicular. Okay? So no matter where we rotate this loop, you're always going to have a force that's constant. And it's going to be equal to B and I and L, the length of the wire that's in the external field that's produced by the magnets. Okay? Let's just draw a top-down view of our loop. please. So here I'm going to have my length. I'm going to draw in my axis of rotation down the middle. And up the top, I'm going to have width equals 2r. So obviously we have the dimensions of a rectangular loop. It's got a certain length and it's got a certain width. Okay? Let's just write out what we've got available to us. On our data sheet, we have the following. You've got torque equals Rf. Perp, and you've got F equals BIL. In fact, it's B perp, I believe. There's a perpendicular symbol attached to B. That's it. We need to go a little bit further than that to get the torque because there's a few things missing. What we want is your Lorentz force is actually NBIL, where N is the number of turns. Because what we can do, I've just got one wire. I bent it into a rectangle and it returned out of the magnets. You could have 2 loops of wire. Instead of it returning out, let's just do another lap around that rectangle. We could have 10 loops, 10 laps. Well, we could have n loops. And the demo that I have here, I haven't counted it, but we might have 100 wires that are looping around. All right, in that case, n would equal 100. You will be told that in a test. A motor, the armature of a motor has 1,000 coils. Well, that's n equals 1,000. Okay? Now, I'm about to show you an equation that must always be derived. Okay? So we could say the following, that the total torque on a loop of wire, okay, is going to be 2 times NBIL, or 2, hang on, just try again, 2 times RNBIL, because I forgot the radius, right? I'm just going to rewrite this another way. I'm going to write this as 2RLBI. I've just take and then there's an N there as well, right? 2RLNBI. But now what we need is to understand that as our coil starts to rotate, the force remains always pointing up. I'm just looking at this section of the wire. The force always remains pointing up. But what's going to happen is as it rotates up, there's now going to be an angle that's no longer 90. I have this orientated at the moment such that the angle between the force and my line of action just happened to be 90 degrees. I need you to visualize that as that coil is allowed to rotate, we're now going to enter an obtuse angle. It's now going to approach 100, 150. It's going to get all the way up until the force is now 180 degrees from our line of action. Yes?
So the force always points up even when it turns around.
Well, we're going to get to a problem with the motor. Once it gets to that situation, we need to do some things to make sure our motor continues to turn. Okay? And in fact, how much room do we have? Leave that little bottom strip free because we're going to draw some orientations of our coil from a different perspective. So I'm just going to add a sine theta.
So how exactly?
Now, hold on. Sine theta is going to be the angle between R and F. Okay, not the angle between I and B. So this sine theta is back to our good old torque equals RF sine theta that we learnt in week 7 of last term. Okay, so that sine theta is the RF sine theta of the torque. Okay, now we can we can hold on. We can look at when this would be a maximum. This would be a maximum when it's at right angles. So it's going to have a maximum value of 2Rn BIL. That's what the maximum is. But as that motor starts to rotate around, we're going to then reduce our torque. It's going to start to reduce by the sine of the angle until it gets to that orientation when it's theoretically or effectively equal to 0. Now, the reason why I wrote 2RL is because if we look over here, we have an equation for area is length times width, which I could write as length times 2R. Okay? So I could replace 2RL with A, area. And I forgot my sine theta there. So you end up with this equation, A, B, I, N, sine theta. So I'm going to write it as B, A, I, N, sine theta. Okay? Bane. So you can remember the enemy from the DC comic book universe. Now, this equation is not in the data sheet. It's one of the three. Oh, I'm running out of room. Holy moly, where am I going to? Oh dear. Oh dear. Save some room there for my little side on diagrams. Just off to the right, just right here, not in data sheet. And so you have to show the derivation, okay?
What is the derivation for that?
We just did it from above. So the derivation would be to go, I'm going to state this equation and this equation, okay? You have to manually realize that there's two torques on each side of the axis, but they happen to be producing the same direction of torque. That's why we're doubling it. So on one side, it would be just RNBIL, but on the other side, we have an RNBIL, and they're in the same direction. So that's where the 2 came from. And then you can go, all right, cheeky little trick here, 2RL, well, that's the area. So have a think. I could increase the area of my coil. That would increase the torque. There are limits, obviously. There's limits of how large you can cram stuff in to your external magnetic field. You could increase the number of turns. Each turn contributes to a certain amount of torque. So if we could double our turns, we double our torque. More current. Well, if we had more current flowing, there would be more Lorentz force, so there would be more torque. And the stronger magnetic fields. Now, we're going to look at different ways to make magnetic fields. Currently, this demo has permanent magnets sitting outside of our coil, but there are other ways. Remember, this sine theta is the angle between the force and the line of action. Okay? Just one last thing. And I'm running out of room. We could exchange this. So sine 90 equals 1. So we could then go the maximum torque is simply going to be that. Okay. So you've got to be careful whether they give you the orientation already at maximum torque, or maybe they're nasty and they have the plane of the armatures tilted a little bit, and you've got to figure out what the force is. Okay. Now, let's just follow this logic along. So I apologize if you've used the bottom of page 33. Draw really, really small. Let's just look at a few different side-on orientations. So down here, let's just say currently, what? Oh, if I looked side-on, then this is what we'd have. We've got our pivot point in the middle. We've got R. That's an R, by the way. Okay. So this is me looking at this wire. So the current's going up that way, down that way, and I'm looking sort of through the guts. Well, we would have a Lorentz force going this way and a Lorentz force going that way. Mind you, our magnetic field is still traveling left. Okay, so right grip rule, fingers that way, thumb that way. Cool. We've got a torque. Okay, now in this case, theta equals 90, and so we have our torque equals maximum. Lowercase n, capitals for everything else. Now, here's the issue. Let's follow this progression. Let's allow this coil to rotate. I'm just changing my mind, and apologies for disturbing you. Let's allow it to rotate by about 45 degrees. So I'm going to take this original plane and I'm going to rotate my top wire around by about 45 and the bottom wire around by about 45. Okay? So there's my 45 degrees. Remember, the Lorentz force does not change because the current is still, even though it's rotating around in this merry-go-round, it's still at right angles to the magnetic field. Okay? But now we've introduced an angle that is no longer 90 and it's no longer maximized. So this angle here would be 135. Okay? Would somebody mind telling me what the sine of 45 degrees is? No. This is physics, not maths. Evaluate it numerically.
0.7.
Larry, what's sine of 45?
0.707.
Thank you. Of the maximum. All right, so our torque has reduced. Okay? It's getting less and less and less. So, sine of 135. Now let's take it to the extreme and rotate our coil from the original. We're going to now rotate this to 90 degrees. Now at this point, I'm running out of room. The Lorentz force is still the same, still constant. Okay? But now what we've done is we've introduced an angle of 180 degrees. So our torque is at 0. Okay? Now if nothing changes, what would happen is that coil, as it's rotating, it's gaining some rotational energy, right? So it's going to, like a kid, you let go of a kid on a swing, they swing down to the lowest point, they've got kinetic energy, they swing past that point. So your coil would want to wobble. It's slowing down, because imagine if we kept going, the first two diagrams are showing a clockwise rotation. If we went to the other side, so if our coil crosses that now, it's going to try and twist it backwards. So it's going to rotate clockwise, and then it's going to wobble anti-clockwise, clockwise, and it's going to end up just getting stuck. It'll lose all of that kinetic energy due to heat and friction, and you would just eventually be left with your coil just stuck vertically. Okay? Now, yes, technically the two ends of the two lengths of the coil would want to be pulled apart, because the Lorentz force is trying to pull them apart. Okay? We're back to two parallel wires, the idea there. So we need something to fix that. But before we do so, could we go past those wonderful diagrams Why the hell have I got... Oh, is that where I was going to rotate? Is that where I was going to draw my diagrams? I hope not.
So do we have to write taking moments about A when we're doing questions like these?
Oh no, hang on, sorry. We seem to be missing a page. Oh boy.
The electromagnetism.
Alright, let's not get to the problem yet. Let's just consolidate the equations that we've learnt, okay? Let's consider this question on page 37. We have a coil of 100 loops. We've got our area, but be aware, I've thrown in some unit prefixes of centi. You need to convert them. We've got our magnetic field strength, again, unit prefix of milli. We've got our current. Okay? To make this question understandable, let's just quickly sketch in a magnet and draw in our coil. All right? So by drawing north there, remember field lines external to a permanent magnet go from north to south. Okay? And then to change things up, let's put the current going this way. Okay? So basically, this question, you wouldn't know the direction of rotation unless you had some diagram to investigate. So, pick a side of wire. Doesn't matter whether you pick the right side or the left side, you need to use the Lorentz force. Figure out the direction of that Lorentz force, and then you can draw in the rotation. Okay? So once you've finished that sketch, so we're trying to answer the first instruction, the direction of the rotation. So my fingers pointing left, my thumb on the right-hand side is pointing into the page, my palm on the right side of the coil is being pushed upwards. All right? So all I need to do is draw in my force on that side. You could draw in your force on that side. So from our perspective, it would be seen to rotate anti-clockwise. Okay? Are we all happy with that?
Yes, sir.
Wait, which? Oh, that's going back.
So you could look at the left side. All you would change is your thumb points towards us, fingers pointing left. That side of the wire is going to get pushed down. Okay? And we happen to be at the orientation of that coil is such that we're at maximum torque. Because you would notice that the force is at right angles to the line of action. Okay?
So would you have to be told which way? Given a diagram?
Yes, you would need a diagram. Yep.
Or could they tell you the direction current?
You could be nasty. You could be given the terminals, positive and negative, and you'd have to then go, well, the positive charge goes from the positive terminal. You're just doing one extra step to figure out the direction. Okay, the force on one side length, that's a bit boring. F equals NBIL. Again, that N is not in the data sheet, so please remember it. 100 times 10 to the negative 3. There's my milli, my 3 amps, and just please be careful that you do not confuse length and width. All right, so the length is generally going to be the length that's inside and perpendicular, and the width is generally the section that's parallel to the magnetic field. So we want the length 8 centi. Okay, so I could do a bit of cancel 0.1 cancel 0.1 times 3 times 8. It's 2.40. Okay, on one side. We're not told which side, so we can't say up or down. Now, we've got options here. If we want to do the total torque, we could go T total equals Bain sine theta. So we could go our 100 milli. Now, area, length times width. So we've got to go our good old, I'm going to be lazy here and just go 0.08 times 0.04 times our current times our N sine 90. You throw all that in, it will give you the total torque as 9.60 times 10 to the negative 2 Newton meters anti-clockwise. Okay. So that is a perfectly acceptable, but remember, what do we have to do? Show that derivation. Okay. Now, you might get to the WACE exam and they might go, yep, pay it, but just be careful. The other option is you could take your force and go that your total torque equals 2RF, right? Remember, you've got RF on one side, RF on the other side, and they're going to rotate. So you could go to, R, another side mission here, is going to be 4 on 2. So again, just be careful. We were given the whole width. We were given the width of this coil, but the radius is the distance from the axis. That's our line of action. So again, be careful. If your coil is 4 centimeters wide, then your radius is going to be 2 centimeters. Again, you're doing exactly the same mathematics. You're just doing it in 2 steps instead of 1. Okay? So you'll get the same 9.60 10 to the negative 2 Newton meters anti-clockwise. We will have to get to this wonderful demonstration on our next lesson, which is our last lesson for the week. I'll see you guys tomorrow, period 2. We've got extended homeroom. We'll check out what this thing's going to be doing tomorrow, okay? No, I want the surprise. Sometimes it's good to wait.
It's just going to spin.
Abstinence.